We'll now continue by discussing polynomial rings and then integral domains. To begin, we'll note that to any ring, it is possible to associate another ring, R of x, which is called the polynomial ring, over any ring R. The elements of this ring are polynomials of the form p of x, which are formal expressions, a0 plus a1x plus a2x squared plus an x to the n, with coefficients aj, which are taken from R. These can be written more succinctly as p of x is the sum from 0 to n of a sub j x to the j, and if a sub n is not equal to 0, the polynomial is said to have degree n, where the term an x to the n is the leading term of the polynomial, and the coefficient is called the leading coefficient. The ring R is naturally embedded as a subset of the ring of polynomials over R by viewing any a in R as a polynomial of degree 0, i.e. that each of the x terms has a coefficient of 0, which is clearly an element of R since it's a ring. You can check the algebraic operations on them, but they follow as normal polynomial operations, such as the sum and product of two polynomials. We'll note that two polynomials can always be written of the form p of x is the sum from 0 to n of a sub j x to the j, and q of x is the sum from k equals 0 to n of bk x to the k for some integer n. And since some of the coefficients, where some of the coefficients aj or bk can be taken to 0, we define the polynomials, as mentioned before, in the standard way by simply summing the coefficients on like powers. Likewise, we can take the product by multiplying them out, which is the same as taking the sum over all pairs jk from 0 to n of a sub j b sub k for x to the j plus k power. It is easy to verify that these two operations will function as operations of addition and multiplication on the ring R of x. In that ring, the additive identity is given by 0 of the ring R and the multiplicative identity 1 of the ring R. We will note that some rings, as example z mod 6, namely the integers mod 6, there are certain non-zero elements, such the equivalent class a of the integer 2 and the equivalence class b of the integer 3, for which the product a times b is equal to 0. However, in these, such elements could not have multiplicative inverses, because that would imply b is a inverse a times b is equal to a inverse times ab is equal to a inverse times 0 is equal to 0. That b is equal to 0, which is a contradiction since we chose b non-zero. A ring for which ab equals 0 implies a equals 0 or b equals 0, the zero product property, is called an integral domain. You can check that any ordered ring R is an integral domain, because if R is an ordered ring, then if a and b are in R and neither of those is 0, then a has inverses, then either a is in P or the inverse of a is in P, the positive elements of R, and b is in the positive elements, or negative b is in the positive elements. Therefore, so for some choice of signs, the product plus or minus a times b is equal to plus or minus a times plus or minus b, which must be in the positive elements. Therefore, a times b cannot equal 0. An integral domain for which the cancellation law holds, i.e. if a times c equals b times c, where c does not equal 0, then you can write that 0 is equal to bc minus ac, which is equal to b minus a times c, and since c is non-zero, it follows that b minus a is 0, so b equals a. It's fairly clear that in any field, it must be an integral domain, because fields have inverses with respect to multiplication. However, there are integral domains, such as the ring of integers z, that are not fields, or as we mentioned, that we have integers being integral domains but not fields. However, we can actually see that integral domains can be extended to a field. This will be called the quotient extension of the ring. To see this, we're going to consider the Cartesian product of R cross Rx, namely Rx is the set of R excluding its additive inverse 0. That is, R times Rx is all pairs AB, where A and B are in R, but B is non-zero. And on these, we define the operations of addition and multiplication by A plus B, AB plus CD is equal to AD plus BC over BD, and AB times CD is equal to AC comma BD. You'll note that I said over, because the most natural way to view this, if you note the footnote, is by considering AB to be the fraction A divided by B and CD as the fraction C divided by D. And that will give you this expression for summing fractions and this expression for multiplying fractions. We'll then note that in that we get natural equivalence relations on the set R cross Rx. Namely, if we continue with the example of fractions, 1 over 2 is equivalent to 2 over 4 because they both represent the fraction 1/2. So we set a1b1 equivalent to a2b2 if and only if a1 times b2 is equal to a2 times b1. It is easy to check that this is actually an equivalence relation because it's reflexive and symmetry. It's reflexive and symmetric by, just by looking at it. But for transitivity, if we have a1b1 is equivalent to a2b2 and a2b2 is equivalent to a3b3, then a1b2 is equal to a2b1, and we have that a2b3 is equal to a3b2. So if we multiply the first equation by b3, we get a1b2b3 is equal to b1a2b3 is equal to b1a3b2, and therefore we can subtract terms to the left and we get a1b3 minus a3b1 times b2 is equal to 0. So a1b3 minus a3b1 must equal 0 by applying the cancellation law or the zero product property, since b2 is non-zero. It is then an immediate consequence of this definition of equivalence that ab is equivalent to a times c, b times c, if c is non-zero. As our example, 1/2 is equivalent to 2/4 because we can multiply by c is equal to 2 on top and bottom of that fraction. This is a very useful operation when dealing with this particular equivalence relation. We can also check that addition and multiplication on this product R cross Rx preserve the equivalence classes in the idea that if two elements are equivalent, then their sum is equivalent, i.e. that a1b1 plus cd is equivalent to a2b2 plus cd, and the same for products. Therefore, these operations can be defined on the set of equivalence classes as opposed to just the elements themselves, and we can verify that this is a ring under these operations, where we have the additive identity element is the equivalence class of 0, 1, namely 0 divided by 1 is 0, and that makes sense, and the multiplicative identity is the equivalence class of 1, 1, or any two elements where the top and bottom are equal. We also have the additive inverse element of AB, which will denote minus AB, is the equivalence class of minus A comma B. And we'll note that if we add minus A comma B to AB, then we'll get 0. Namely, we'll get an element that's equivalent to 0, 1. A slightly complicated case in verifying that this is a ring is checking the associative law of addition, where you get this large expression here, but you can check that each of these steps makes sense. Finally, we will note that we actually get our field, as we've been trying to do, by quotienting out R cross Rx by the equivalence class we've defined. And the set of these equivalence relations is then a well-defined ring. And if A is non-zero and B is non-zero, then we have BA times AB is equal to A times B, comma A times B, which is equal to 1, 1, since the product is non-zero in an integral domain. Thus, BA is the multiplicative inverse of AB, and so F is a field. That is, we verified that there exists multiplicative inverses, which is what we need to confirm in order to prove that a set is a field. Since if it's a ring, then it already has additive inverses. This field is called the field of quotients of the ring R. That is, for any ring, we can perform this process so that we get a field. We can then associate to this ring a mapping from the ring to the field of quotients over that ring, namely phi, which sends an element A in R to equivalence class phi of A within F, which is the element A comma 1. And this makes sense in terms of our fraction example, because A divided by 1 will just be A in the standard real numbers. A comma 1 is an element of the field of quotients, or of the Cartesian product, and it's clearly injective, since it'll send different elements to different elements, and we have that it respects addition in this way and multiplication in this way. Therefore, we can realize R as a subset of the field, such that the algebraic operations of R are compatible with those of F. That is, the operations we defined on R are the same operations we'll define on F, and continue as per usual. We'll stop here and we'll continue next time by considering what happens if we perform this operation, form the field of quotients, using our ring being the integers which we just constructed. And with this, we will construct the rational numbers. Thank you, and thank you for watching.